Hi guys, my name is Peter C. Dogba Jr., mathematics instructor at the University of Liberia and your math tutor. In my today's lesson, I will be looking at differential equations and I will be solving the 19th problem on a variable separable. So in the previous lessons, I did a lot of other problems that you can go through to practice. So this is kind of a static problem that we need to look at carefully. So don't panic, let's go through the problem. So we said from previous videos that variable separable is a method used whenever you have a differential equation and you are capable of separating all of the x variables from the y variables, or from all set of one variables from the other set of variables, because it doesn't only have to be x and y, it could be y and t, it could be just every other variable that could be used in the problem. So let's get started. Now we have this differential equation dy by dx equals 1 plus 2 sine of y plus cos of y, 3 plus 2 sine of x plus cos of x. So the first thing we need to do is to ensure that all of the expressions in x are one side and the expressions in y are one side. So we cross multiply. So we have 3 plus 2 sine of x plus cos of x times dy, and then equals this time this. So it's 1 plus 2 sine of y plus cos of y dx. So now this is x, so we don't need, we need to have all x here. So we can divide this out by 1 plus 2. So let's push it small. 1 plus 2 sine of y plus cos of y. We do that on the other side of the equation. So we have 1 plus 2 sine of y plus cos of y. Likewise, we don't need x here. These expressions are all in x, so we must divide it on both sides. Sine of x plus cos of x. So this will carry this one out. And then we do the same on this side as well. 3 plus 2 sine of x plus cos of x. So this one will carry this one out as well. So we will now have dy all over 1 plus 2 sine of y plus cos of y equals dx all over 3 plus 2 sine of x plus cos of x. So at this point now, since the variables have been separated, we need to find the general solution by integrating both sides of the equations. So what we can do, we can bring in some substitutions for sine of y, cos of y, sine of x, and cos of x. Since this is 1, we know that 1 is equal to cos of y, cos square y plus sine square y from the Pythagorean identity. But since the angle that we want to deal with is like half angles, so that we can be able to solve this integral problem, we can divide all sides by 2. So we have 1 to be equal to cos square y over 2 plus sine square y over 2. So this is the first formula that we need. The second one is that for this sine of y, we know that we can bring in the two identities, that is the double angle identity for sine and cosine. We know that sine of 2y is equal to 2 sine of y cos of y. So if we divide both sides, all angles by 2, we will have sine of y now to be 2 sine of y over 2 cos of y over 2. So this is another one that we want to use. Similarly, cos of 2y is equal to cos square y plus or minus sine square y. So if we want to have half angles, so we can divide all sides by 2. We have cos of y to be cos square y over 2 minus sine square y over 2. So this is going to be the third equation that we want to use. Now, for the right hand side, we can bring in other formulas. Now, we know that sine of x is also equal to 2 tangent of x over 2 or over 1 plus tangent square x over 2. Now, we know this identity, right? From yeah, from way down the line. Yes, we know this identity. So also we know that cos of x is the same as saying 1 plus or 1 minus tangent square x over 2 or over 1 plus tangent square x over 2. So we know that for cos as well. So with these fundamental identities that we have, we can now replace them within the problem. So I'm just going to erase only this portion. Okay, let me just take the problem of it. That's we already know. Okay. So you have to be very careful when you're dealing with problems or such before you make mistakes. Because if you miss a kind of sign, you miss a number, just miss anything, you're going to mess the whole problem up. So we have the integral of this one now. You have dy divided by, now 1, we say 1 is equal to cos square y over 2 plus sine square y over 2 plus 2 sine of y is just this one now, which is 2 sine of y cos of y, and then plus cos of y. So cos of y is just equal to cos square y over 2. Okay, so all of these over 2. So cos square y over 2 minus sine square y over 2. So you see that this sine square y and this will go out. So on the right hand side, we have the integral of dx all over. So it's 3 plus 2. Now sine of x. So sine of x is just equals to 2 tangent of x over 2 or over 1 minus or 1 plus tangent of x over 2. And then plus cos of x. So cos of x is just 1 minus tangent square x over 2 or over 1 plus tangent square x over 2. So we can further simplify. We have the integral of dy all over, and this is already 4. Now this one and this can be added, so it's like 2 cos square y over 2, and then 2 times 2 is 4 sine y over 2 cos y over 2. And then on the right hand side, we have the integral of dx all over. Now we can simplify this kind of complex fraction. So we're gonna have this to be our second denominator, kind of that. So the LCD for these three, 1, 2, 3, is just 1 plus tangent square. This is square, please. Tangent square x over 2. So 1 into this is just this whole thing. So it's like this thing multiplied by 3. So it's like 3 plus 3 times this is 3 tangent square x over 2. And then plus, so 1 plus tangent square x over 2 goes into 1 plus tangent square x over 2 is just the same. It's just 1. So it's like multiplying the numerators now. We have 2 times 2 is 4 tangent of x over 2. And then plus, so this goes into this is just 1. 1 times this is just 1 minus tangent square x over 2. So, so this expression down here can go within the numerator, complex fraction. And then we can simplify it further. So we have the integral of dy all over. Now 4 and 2 and 4 we can factor out. So if we factor out, we will have 1 over 2. So we just have cos square y over 2 plus 2 sine y over 2 cos y over 2 equals the integral of, so we like bring this one up, 1 plus tangent square x over 2 dx all over. Now, so we take the square one first. So it's like this and this. So it's 3 minus 1. So it's just like 2 tangent square x over 2. And then we come to this one plus 4 tangent x over 2. And then 3 plus 1 is 4. So we can, now for this 1 plus tangent square x over 2, we know that secant square x over 2 is equal to 1 plus tangent square x over 2. So we know for the derivative, if we allow our u to be tangent, if we differentiate tangent, we get secant square x, right? So since we want to allow our u to be tangent, then it means that we must bring in the identity for this 1 plus tangent square x over 2. Likewise with this one, if we divide all side by, we divide this side by cos square y over 2, cos square y over 2, and then we come up here, we say cos square y over 2. We have not changed anything in the problem, because just look here. If we have 1 over cos square y over 2, divide by, now this is 1 over cos square y over 2. You change this sign to multiplication and reciprocate, you have cos square y over 2 or over 1. So this and this cancel, you just left with 1. So you've not changed anything in the problem. What you're trying to do is to ensure that you rewrite this expression so that if you allow your u to be something down in the denominator, if you differentiate, you will have what you need up within the numerator. So 1 over cos, we know that is secant square is 1 over 2. So this is secant square y over 2 dx or dy. So cos and cos is just 1. This is 2 tangent. Now, look here now. Let's pay keen attention. So this can cancel 1 from here. You'll just be left with cos y over 2. So sine of y over 2 divided by cos of y. Sine over cos is equal to tangent. So this is just tangent of y over 2. So in this case, now we can say let u equals to 1 plus tangent of 1 plus tangent, let's say 1 plus 2 tangent of y over 2. Such that if we differentiate the u, differentiate this expression, we have the u equals to, this is 0, 2 secant square y over 2 times the derivative of y over 2, which is just 1 over 2. So now this is equal to, so this numerator now is just secant square x over 2 dx all over. Now you have 2 times tangent of x over 2 all square plus 4. Now let's just factor out 2. 1 over 2 comes outside. So this guy is just out. This one will reduce to 2. And then you have tangent of x over 2. And then plus this one will reduce to just 2. Right? Instead of 4. Okay. So here we can say let u, or let's use v now. Let's v equals to tangent of x over 2. So the v now will be, what is it? The v now will be secant square x over 2 times the derivative of x over 2, which is just 1 over 2. So let's erase the top portion. So now for this one, we have the u equals, now this is So this is 2 and this is 2. The 2 and 2 go out. So we just have secant square x over 2 and then attach the y to it because you differentiated with respect to y and we differentiated here with respect to x. So this is just dy. So this is the first one that we're going to replace. And then the second area we have dv now. So this 2 times this is 2 dv equals to secant square x over 2 dx. So go back to the problem. What is this is a problem? 1 over 2. The integral of this whole numerator now is just equal to the u. And the denominator now is just equal to u. Equals, this is 1 over 2. The integral of, now this numerator now is just 2 dv divided by the denominator now, this is u square or v square plus 2v plus 2. So we have to be very careful before we make some of the signs. So this and this cancel. Now this is just 1 over 2, the ln of u. For this area now we have dv all over. Now we can open up this so that we can be able to factorize it. We know that v squared plus 2v plus 1 plus 1. So you see, you can factorize this now. So this is ln of u raised to the power 1 over 2 equals the integral of dv all over. And this is v plus 1, v plus 1 plus 1. So we can bring this on the side. We got ln u raised to the power half equals to the integral of dv all over v plus 1 raised to the power 2 plus 1 square. Now I said 1 square because I want to bring in a property. The integral of the dx all over x squared plus a is just equal to 1 all over a tangent inverse of x over a. So this is similar. Our x here is representing v plus 1. So you have the ln of u to the power half equals. So we can integrate now. This is 1 all over a. This is our a1. Tangent inverse. Now let's see. Where is it? I hope all of these expressions are all intact. Okay. So we have our tangent inverse now of, what is our x? Our x is v plus 1, right? And then divided by a is just 1, plus some arbitrary constant c. So now we have the ln of u raised to the power half equals to tangent inverse of, what is v? V initially was this tangent, was tangent of x over 2 plus 1 plus some arbitrary constant c. Lastly, what was u? U was this. U was just equal to this one. So we have the ln of, so u now is 1 plus 2 tangent y over 2. So we can take the square root of it because this means square root, equals to tangent inverse of tangent of x over 2 plus 1 plus some arbitrary constant c. So this is how we find the general solution of this differential equation using variable separable. So thanks so much for watching. Please subscribe to our YouTube channel, like our videos, share the videos, hit the notification button so that you get updates from our new videos. Thank you. See you during our next lecture.